Welcome to Chapter 6.1. We'll be working with quadrilaterals. Our vocabulary list for this lesson: consecutive sides and angles, opposite sides and angles, the definition of parallelogram, rectangle, rhombus, square, kite, and trapezoid. Many of these you already know. So let's talk about what a quadrilateral is. A quadrilateral has consecutive sides that intersect at the vertex of the quadrilateral. So what we're talking about is, as an example, side JK and side KL. They are next to each other. They are consecutive sides. You would, if you were calling out this quadrilateral JKLM, you would move from J to K, K to L. They are listed consecutively. Opposite sides have no points in common, so JM and KL will not be touching each other. Consecutive angles will be angles whose vertices are the endpoints of the same line segment or the same side. So, as an example with line segment JK, you would have angle J and angle K at the endpoints. So, if I were naming the angles in this quadrilateral, I would be saying JK, LM, and J and K would be consecutive to each other. K and L would be consecutive, L and M would be consecutive, and M and J would be. Opposite angles are angles that are not on the same side of the quadrilateral. This is similar to what we've seen in other figures. In this quadrilateral, J and L would be opposite, K and M would be opposite. Our first subset of a quadrilateral is the parallelogram. A parallelogram is a quadrilateral with two pairs of parallel opposite sides. We can see from this drawing that XW is parallel to YZ. We can also see that YX is parallel to ZW. The sides do not have to be the same length. However, they do have to be parallel to each other. There will be 4 of them, and they will be named the parallelogram consequently. Now let's take a look at another quadrilateral that is also a parallelogram. However, it's a parallelogram that has 4 right angles. And you're familiar with this shape. This is a rectangle. So a rectangle is a parallelogram with 4 right angles. We have the rhombus. The rhombus is a quadrilateral, but it's also a parallelogram because it has 2 sets of parallel sides. It also has 2 sets of congruent sides. All of these sides happen to be the same length. But if you can tell from the drawing, this is not what we're familiar with as a square. It does not have 90-degree angles. Be sure to put that in your notes. So a rhombus is a parallelogram with 4 congruent sides, but it does not have 90-degree angles. And this is a quadrilateral that is a parallelogram. That is also a rhombus, and its subset is the square. And it has the 2 sets of parallel sides. Each side is the same length, but it has 4 90-degree angles. We have a shape here. You probably don't see this very often, but this is called a kite. And a kite is a quadrilateral with 2 pairs of congruent consecutive sides. but whose opposite sides are not congruent. So LM is congruent to LO, and NM is congruent to NO, but they are not congruent to each other. This is what creates this kite-type shape. Take a careful look at the congruency marks here and note that opposite sides will not be congruent in the kite. Our last shape is the trapezoid. The trapezoid is a quadrilateral. It is not a parallelogram. It only has one pair of parallel opposite sides. So a trapezoid has one pair of parallel opposite sides. The other sides will not be parallel and do not have to be congruent. Some interesting facts about this trapezoid: the parallel sides of the trapezoid are called bases. So KJ and HI are called bases. The other two sides, KH and JI, are called legs. If the legs are congruent, then the trapezoid is called an isosceles trapezoid. Think about the shape that you have for an isosceles triangle. In fact, this is an isosceles trapezoid, this drawing, and if I were to extend these two sides, KH and JI, they would meet and you would have an isosceles triangle. So let's take a look at our categories here. Our overall category is the quadrilateral, which is the polygon with four sides. You have a subset of parallelograms, and in parallelograms you have the rectangle, rhombus, and square. The kite stands alone. The trapezoid also stands alone, but it has a subset of the isosceles trapezoid. Let's look at example 1. To which of the defined subsets does each quadrilateral appear to belong? Label all categories that apply. Anytime in your homework that they're asking you to label these shapes, they want all the categories that apply unless they say otherwise. So these are shapes that appear to have, this one, A, appears to have two sets of parallel sides, so we'll call it a parallelogram, and the sides appear to be the same length. So this would be a parallelogram and a rhombus. So it would have two pairs of parallel opposite sides and four congruent angles. B would be a trapezoid with one pair of parallel lines, and WX and ZY appear to be about the same length, so we'll call this an isosceles trapezoid. Example 2. Thinking about what we know or have just learned about kites, find the measure of each side of the kite. So one of the things that we know about kites, and your drawing does show that there is congruent sides KJ and MJ. But if this is a kite, then that means that KL is congruent to LM or ML. So now when we figure out the math here, we have to keep those things in mind. So let's begin with the two sides that they had marked in the drawing. And JK is congruent to JM. So x plus 5 would be congruent to 3x minus 1. That gives us x equals 3. If we solve the other two sides, their variable is y. So we have KL is congruent to ML. That's 3. Y plus 2 equals 5y plus 2. And your answer would be y equals 2. If we go ahead and use substitution, we find that we have correct answers because both JK and JM equal 8, and KL and ML equal 12. Example 3. State the most specific classification for quadrilateral A, B, C, D. So what they do is use coordinates for this quadrilateral, and point A we can see is at -3, 0. Point B is at -1, 3. Point C is at 2, 1. And point D is at -2, 0. So we have our points, and it asks us to, number 1, find the slope of each side. So you take a look at this, and I'm going to just eyeball this right now, and I'm going to state that BC equals AD, which is its opposite side. So let me see if I can find a place where I can mark this without interfering. And we need to figure out what the slope is. So the slope of BC and AD are both -2/3. Now let's look at the slope of measure side AB and the measure side CD. And the slope of AB and CD will be equal, and they are 3 seconds. Now, -2/3 times 3 seconds will give us -1. So, if you remember back to when we were doing slopes, slopes that are opposite inverse are perpendicular lines. So that means that we actually have 4 right angles here. We can't prove at this point that this is a square, but we can state that it is a rectangle. So rectangle ABCD with opposite sides and consecutive perpendicular angles that are 90 degrees. Now it asks us to find the length of each side. You use the distance formula to find the length. So AB would be the square root of 2 squared plus 3 squared, which is the square root of 13. And side BC equals CD equals DA. And we can state that, therefore, that ABCD is a square because all 4 sides are congruent. And this symbol here should say congruency, not incongruent. Now, how did I find out what that length was? I did the distance formula. I have it over here to the right if you need to refresh. And that's using the points. So probably the first thing you should do with your drawing is label the points that I called out. So once again, using analytical geometry and a graph, you would find the slope of each side. That will determine whether you have perpendicular sides, parallel sides, and so forth. And then you'll find the length of each side using the distance formula. Our first theorem for this chapter, Theorem 6.1.1, Quadrilateral Angle Sum Theorem. And we can see our drawing of the kite. We have kite JKLM, And our theorem tells us that the sum of the interior angle measures of any convex quadrilateral is 360 degrees. In previous chapters, we studied theorems about the relationships of angles and triangles. Now we're going to study the relationship of the interior angle measures of quadrilaterals. One point to remember is that the diagonal of a polygon is a segment connecting non-consecutive vertices. So in this drawing, we have JL, and it is a diagonal of this kite. Dividing a convex quadrilateral into two triangles using diagonal leads to the theorem. So what you've done when you've drawn that diagonal is formed two triangles that share a side. So when a quadrilateral is divided by a diagonal forming two triangles, that should lead us to understand that by adding the two triangles, and remember each triangle has 180 degrees, we will have a total of 360 degrees. So 180 plus 180 is 360. And this is just a generalized theorem, our next theorem for the interior angles of any polygon. So we just did the four-sided polygon. It had four sides, two triangles, and its angle measures were 360 degrees. Now what happens if you have more sides? Well, if we have five sides and we go ahead and draw diagonals, example is right here in the drawing, you'll end up with 1, 2, 3 triangles. 180 times 3 will be 540 degrees. If you have six sides, like this drawing, and you draw diagonals, you'll have 1, 2, 3, 4 triangles, and 180 times 4 is 720. So this leads us to actually be able to create a formula. We see the number of sides minus 2 is how many triangles we'll have. So we'll call that n minus 2. And if you multiply that answer by 180, you get the sum of the angle measures. So the formula for the sum of the angle measures of a polygon, and this includes a triangle. Remember, a triangle is a polygon, is n minus 2 times 180. Theorem 6.1.2, convex polygon angle sum theorem. So the sum of the interior angle measures of any convex n-gun is n minus 2 equals 180. To solve for each angle of a regular convex n-gun, use n minus 2 times 180 divided by n. So if you have a square, it will be 4 minus 2, which is 2 times 180, and to solve for each angle, that would be divided by 4. So let's see what that would look. So 4 minus 2 times 180 divided by the number of sides would equal 2 times 180 divided by 4. 360 divided by 4 would be 90 degrees. And I did say it was 4 sides, and we are talking about regular n-gons. So regular would mean the angles would be congruent, the sides would be congruent, and we know that in a 4-sided figure where those properties were true, we would have a square, and we already know that squares have 90-degree angles. So example problem 15 and 16 on page 252. Find the sum of the measures of the interior angles in each convex polygon. Use n minus 2 times 180. So if a decagon, which has 10 sides, were used, we would have 10 minus 2 times 180, which would be 8 times 180, which equals 1440 degrees. If we want to find the measure of an interior angle of each interior angle of a polygon, then we would take that same formula and divide it by the number of sides. So let's use a pentagon, which is 5 sides. 5 minus 2 is 3. 3 times 180 would be 540. Divided by 5, you would have 108 degrees in each angle in a regular pentagon. So what is the sum of the measures of an external angle from each vertex of the quadrilateral below? Let's look at these quadrilaterals. They're all different, and you can see that each external angle is marked. In the first drawing that we have here, the sum would be 360 degrees, 65 plus 75, 113 plus 107. What would be the sum for the triangle? Well, the triangle is 134, 71, and 155, which is 360. Seeing the beginnings of this pattern, what conclusions can we draw? Well, we could accurately conclude that if we have a pentagon here and we added 5 exterior angles, that their measure would be 360 degrees. This leads us to the next theorem, theorem 6.1.3. The sum of the measures of an external angle from each vertex of a convex n-gon is 360 degrees. This n-gon does not have to be regular. And remember, this is for external angles. So let's take a look at your homework. Your homework is on page 252 and 253, numbers 1 through 15, 20 through 23, 30, and 34. And we also have an extra credit problem on the last slide. I did already demo one of these problems. Number 1 through 5, just some hints. Name the pairs of angles or sides. So example would be AB and CD. Please write it like that on your paper. Number 6 through 13, name all the subsets of quadrilaterals that apply. Don't just call it a quadrilateral. If it's also a parallelogram and it's also a rhombus, please name it that way. For number 23, that will be worked just like example 3. Number 30, use theorem 6.1.1 to complete that. Number 34 is also like example 3. If you have any difficulties, be sure to contact me, and here's the extra credit problem. Find the value of each variable, find the length of each side of isosceles trapezoid HIJK, and be sure to mark congruency marks on this drawing as you work it. God bless.